Hello, everyone. It is the Prophet Michael David, aka Aries, and I hope everyone's having a great day. All right, full disclosure, we're going to be switching back to religion next because of the whole crisis in the land you all call Israel right now. But this video is going to be all about geometry and addressing the thumbnail. As you can see, the primes numbers in blue and the n log n, which is Gauss. We're going to talk about that in a second. But then there's one that's unlabeled that you can barely see, and that's only because the primes track almost exactly on top of that. And that's my line. So that's the thirst trap for this video to get you watching longer. What is the equation of that line? Again, because I've learned from just by looking at some demographics of my own videos and stuff, and that you all don't watch these videos that long, so you got to get to the point. So here's who we're chasing today. If you watched my last video, you will know that is Carl Friedrich Gauss. He is one of the greatest mathematicians in history. And as I described in the last video, a lot of pure mathematicians would consider him number one on their list. He's number three on mine. So today, specifically, what we're trying to disprove or improve upon, however you want to consider it, is his greatest legacy, what's called the prime number theorem. And here it is from Wiki. All right, you mathy people probably already understand the prime number theorem, but for you non-mathy people, it's just basically how dense the prime numbers are in the regular numbers. Number one, that pi symbol from here on out, that's not pi. From here on out, I'm just going to call it the prime counting function symbol or whatever. So whenever you see that symbol 10, like in that example, all it means is that from 1 to 10, there are four prime numbers, 2, 3, 5, and 7. So prime counting function of 10 is 4. Prime counting function of 11 is 5, because then you have 2, 3, 5, 7, and 11. Prime counting function of 12 is also 5. Prime counting function of 13 is 6. So it's just basically a function that logs in a discrete way the density of the primes in the natural numbers from 1 to infinity. So why have mathematicians throughout history, including Gauss, always wanted to do it this way with the density? Well, to put it in a nutshell, is because they want it to be asymptotic, which if you read the whole wiki thing, you can kind of understand, especially the more you know about math. But they like that because asymptotic means it goes to a single value. This all descends from my namesake, one of my namesakes, my first taken name, Apollonius of Perga, who proved that you could conical sections, you can look it up. You could produce a circle, ellipse, parabola, or hyperbola. And all the mathematicians like to deal with the hyperbola. That's the asymptotic. Look it up if you want to learn more about that stuff. But what I did is I went the other way. I went with the equation that makes it parabolic, and mathematicians don't like to deal with that because you have to deal with infinities or something that's going to infinity, not to a single value. What I did is I concentrated on the bottom part of that prime number theorem, and I'll read it to you right now. The prime number theorem is equivalent to the statement that the nth prime number Pn satisfies Pn is roughly equal to n times log of n. The asymptotic notation, meaning again that the relative error of this approximation approaches zero as n increases without bound. For example, 2 to the 10 to the 17th prime number is some really big prime number, and 2 times 10 to the 17th times log of 2 times 10 to the 17th rounds to some other really big number, a relative error of 6.4%. In a nutshell, that's what it is. So n times log of n will always be less than the actual prime number, and the difference increases to infinity, but the percent error goes to zero. So it's 6.4 for that, but as the numbers get bigger, then it's 6.3, then 6.2, but it goes down in a logarithmic way. But full disclosure, I may have just erred in what I said. I'm not going to edit it, but um, I'm not quite sure that the primes value will always be over more than n times the log of n. Just as the equation that I show you, my equation, that the primes won't always be under them. Eventually, they will become so erratic that they will become both less and more than those ceiling and floor values. This will make sense here in the near future. All right, so finally we get to the awesome part, the graphs. So here coming up is a bunch of just graphs from Apple's number spreadsheet, but you can do it on any spreadsheet, obviously. And all it is the primes, which are in blue. Those are the prime numbers, just that I got off the internet, compared to Gauss's equation, n times the log of n. And then the gray line is the one that doesn't have an equation. That's my equation, which I will show you at the end, I promise. Okay, so this first one is just the first 25 primes. The second one is the first 100 primes. The third one is the first 250 primes. This OG screenshot of this video is the first 2,762 primes, which is why my line is pretty much indistinguishable from the prime line. So finally, for all of you that have watched all through this video, or the people that have skipped ahead, what is this magical equation that seems to follow the primes so well? Well, it's this. Now, I was going to stretch this out initially, but I forget how much time is eaten up in these videos. So instead, I'm just going to show you graphs progressively, larger prime numbers, from the prime numbers themselves to Gauss's number or equation, n times log of n, versus my equation. All right, as you can see, that graph is primes from 75,000 to 100,000. And as you can see, the Gauss's number, n times the ln of n, falls off, and the primes fall off for my number, but mine and the primes are really, really close. In that screenshot of prime numbers between 175,000 and 200,000 is even more indicative. My equation continues to tightly bound against the primes, if not always over, but Gauss's number is, or equation, the green line, is almost totally off the graph. So then after the green line is off the graph, the spreadsheet auto scales. And so the last three slides I'm going to show you are just the auto scaling of the numbers, equations, as they go up to 500,000. So as you can see by those three slides, even as the numbers go up, the pattern or the look of it seems the same because Gauss's equation, the n times ln of n, falls off just the same as the prime numbers fall off for my number, and will do so to infinity. And so my equation will follow the prime numbers much, much better, especially when you do it in density values, than n times ln of n. All right, I'm running out of time, so your question may be, is there an end game to this? I mean, if you haven't found the secret to the primes, is there an actual line that tracks the primes continuously from 1 into infinity in this context? And yes, I found that, and this is what it is. Okay. Um, Anybody who's a mathematician or really good at maths will probably understand that equation, but I'm going to put it in layman's terms for the rest of you. Basically, what I'm saying in that equation that is, as the natural numbers go from 1 to 2 to 3 to 4 to 5 to infinity, while at the same time in that equation that v, which stands for variable, goes from pi 3.14 something 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 to Euler's number 2.718 something 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 over the course of that natural affinity, that line will always follow the primes. All right, I'll obviously do a follow-up, also depending on how many comments there are through this video. But as always, God loves you all very much. Rule number 1, do not touch each other without another person's consent, aka do not hurt each other. And rule number 2, it's all about honesty. Lies are a tick down, aka try not to lie. All right, I'll talk to you all later.